Okay, we have discussed this Gaussian random variable in the last class. So it is defined the probability density function px of x as 1 over root 2 e raised to power minus square by 2. This is for 0 mean and unit variance random variable, Gaussian random variable. Okay. Otherwise, if we have a mean value and variance sigma square, then we have defined px of x as 1 by sigma root 2 e raised to power minus x minus m square by 2 sigma square, where mean is m and the variance is sigma square. And then we have defined that how you can find the mean and the variance of this random variable. We have shown that the mean of this is m and the variance is sigma square. And we have also integrated this function, and the integration of the function was 1, so that it satisfies the property of the CDF. Now today we will discuss about the CDF of this function, the cumulative distribution function. Okay, and the CDF of this function, which I will say f x of f, it is nothing but the integral of PDF from minus infinity to x 1 over root 2 pi e raised to power minus x square divided by 2 into dx, or I can write it as 1 over root 2 pi integral of minus infinity to x e raised to power minus x square by 2 dx. Okay. So this is the CDF, which shows that the probability of random variable x having value equal to or less than x is given by this relationship. Now if you want to find the CDF of this Gaussian random variable, we introduce a new function which we call as the Q function, and which is defined as Q of x is equal to integration of 1 over root 2 pi integration of over x to infinity and e raised to power minus x square by 2 dx. Okay, so if you look to this Q function, what actually it represents is that if I have a Gaussian PDF, let us suppose, with 0 mean and unit variance, maybe like this. So the mean is 0 and the variance is 1. And if I say P probability of random variable x having value equal to or less than x is basically given by this integral, and this you can say it is nothing but the integral of your PDF where the limit goes from x to infinity. Okay, so if I say that if I take any point here x, then if I integrate the PDF from x to infinity, that will basically give you the area under this curve, which I call as Q of x. Okay, and definitely the probability of x having value less or equal to x will be given by 1 minus Q of. Okay, because if I suppose take this x here, then probability of x less or equal to x, which is the CDF, that will be equal to the total area under this density function is 1, and this qx, it gives you the probability, it basically gives you the probability of x greater than x. Okay, so if I subtract this area from 1, what I will left with this much area. Okay, which is the probability of x having value less or equal to x. So that is 1 minus q of x. So q of x is nothing but it is the integral of the Gaussian PDF with limits from x to infinity. Okay, and if you define this as q of x, then the CDF of the Gaussian random variable fx of x will be simply 1 minus q of x. Okay, and you can see in the textbooks that this q of x has been tabulated. There is a table where you can find different values of q of x, maybe q of 0, q of 0.01, q of 0.02, and so on. Okay, so like this is the table for q of x. So for x is equal to 0, your q of x is 0. For x is equal to 0.01, your q of x is 0.46. For x is equal to 0.2, and q of x is 0.42. Okay, like that. So for x is equal to suppose 1, q of 1 is 0.1587. So this gives the values of x. Okay, this table gives the different values of x from 0 to 10 with the increments of 0.01. You can also use this row, like suppose if I take this point x value this and this, then it is 0.1 plus 0.09. Okay, so you get 1.09. So this is the value of q function. Sorry, this is the value of the q function at 1.09. Okay, likewise if I take 0.8 from the column and 0.05 from this point, so you get 0.85. Okay, so at 0.85, q of 0.85 will be 1.1977 and so on. Okay, so that is a table which is given in the books, because you cannot find this integral in the closed form, so it is basically computed numerically to find the different values of the q function. Okay, now using this q function, I can say that if this is my PDF, and if you plot the q function for different values of x, q of x, like we have seen here, when you take x as 0, so q of 0 is 0.5. Okay, and then 0.01 is 0.946, then 0.02 it is 0.4922, and so on. It means as you increase x, the value of this q function, it slowly decreases. So at 0 it starts from 0.5, and then as you increase x it decreases, and as this x goes to infinity, definitely it will go to 0, like this. And if you see the negative values, because this table gives only the positive values of the q function, if you want to suppose find the q for -1, q at -1, then q at -1 is simply taken as 1 minus q of 1. Okay. And this relation should hold because if you see q of minus 1 means the probability of or the area under this PDF for the points which are greater than minus 1. Okay, this is what you will get q of minus 1. So minus 1 to infinity, you have to integrate this PDF. That is the area under this curve. And since this Gaussian PDF is symmetric, so if I say this is 1, so the area which is greater than 1, this much, it is same as the area which is less than minus 1. Okay, so the area from minus 1 to minus infinity is same as the area under the curve from 1 to infinity because of the symmetry of this function. Okay, so if I try to find, now I am trying to find q of minus 1. So q of minus 1 is basically, this is PDF and this suppose is minus 1. It means I am trying to find the area under the curve for values from minus 1 to infinity, of course excluding minus 1, but it is for greater than minus 1. Okay, and that will be same as 1 minus q of 1, because q of 1 is the area under the curve from 1 to infinity. This is q of 1. Okay, and if I subtract this area from 1, that is the total area under the PDF, what I will get is this area, the area from this point to this point. Okay, this is 1 minus q of 1, and that is exactly same as q of minus 1, because this area and this area will be same. Okay, because of this method, it means you integrate from minus infinity to 1, or you integrate from minus infinity to 1, or integrate from minus 1 to infinity, that it is okay. That is why you can take q of minus 1 as 1 minus q of 1, likewise q of minus 2 as 1 minus q of minus 2, and so on. And if you use this, you can find the values of the q of x for negative values of x. Okay, so like suppose for x is equal to 1, here's some value. Then for x is equal to minus 1, it is simply 1 minus q of 1. Okay, and as your x goes to infinity, your q of x tends to 0. So definitely when x goes to minus infinity, it will go to 1. So it is basically a function like this, q function. Okay, this is the q function. Then the the CDF of a Gaussian random variable fx of x is nothing but 1 minus q of x. So if this is q of x, then 1 minus q of x will be like this. So when x goes to infinity, this goes to 1. Okay, and when x goes to minus infinity, it goes to 0. So this is how you can find the CDF of this Gaussian random variable. And one more important thing that I need to discuss is, so for a general Gaussian random variable, we have px of x as 1 by sigma under root 2 pi e raised to power minus x minus m square by 2 sigma square. And accordingly, for this function, the CDF of x of x will become 1 by sigma root 2 pi integral of minus infinity to x and e to the power minus x minus m square by 2 sigma square into dfx. Okay, and if you replace this x minus m over sigma with suppose y or z, whatever you write, then I can write this function as 1 by sigma under root 2 pi integration of minus infinity to this x, this limit of x will become, so it is x, now we are replacing x minus y with y, so y will become x minus m over sigma and e to the power minus of this x minus m by sigma is y, so it becomes 0 to the power minus y square by 2 into dx, that becomes sigma times dy. Okay, and this sigma gets somehow cancelled, so you get 1 over root 2 pi integration of minus infinity to x minus m over sigma into e raised to the power minus y square by 2 dy. Okay, and if you look to this function, it is nothing but you can take it as 1 minus q of, you can see here we have taken the CDF. In the previous case, what we have done, one minute, yes, so in the previous case we have taken this as 1 minus q of x when the integration was from minus infinity to x. Okay, it is for minus x square dx, so it was taken as 1 minus q of x. Now in this case, since your integration is from minus infinity to x minus m, so I can write it as 1 minus q of x minus m over sigma. So this is the CDF of a general Gaussian random variable with mean m and variance sigma square. And since this is your CDF of x and it represents the probability of the random variable x having value equal to or less than x, so that is 1 minus q x minus m over sigma, and definitely the probability of x greater than x will be equal to q of x minus m by sigma. So if you get these two, the total probability becomes 1. Okay, now using this relationship we will try to find the probability of this Gaussian random variable, or we will estimate the width or spread of this Gaussian random variable. So now I have two relations, that fx of x less or equal to x is 1 minus q of, which is x minus m over sigma, and fx of x greater than x is q of x minus m divided by sigma. So this is in fact probability of this, probability of x. Okay, this is probability of x less or equal to x, which we call as fx of x CDF. So this is the probability of the random variable having value less or equal to x, and this is the probability of the random variable having value greater than x. Okay, if I want to find the width of this Gaussian PDF, So I have a Gaussian PDF suppose with this is px of x. This is the PDF. So with some mean m and maybe variance sigma. So this is the mean value, and that sigma square with the variance, and suppose this is sigma. Okay. So this point is definitely it is m plus sigma. This width is sigma. Okay. So I call as standard deviation, and the square of this is variance, and this point is m minus sigma. So we will try to find the probability of the random variable, the Gaussian random variable, between m minus sigma and m plus sigma, or m minus 2 sigma and m plus 2 sigma. That what is the probability of getting the random variable x between m minus sigma and m plus sigma? That is mean plus minus sigma. Okay. And to find this, I can use these two as the basic equation. So if I first find the probability of if in this equation, if I let x is equal to m plus sigma, then I will get probability of x less than m plus sigma. Probability of x less or equal to m plus sigma will be equal to 1 minus q of x is m plus sigma. So get m plus sigma minus m by sigma, which is 1 minus q of 1. Okay. So if I let this random variable x takes a value m plus sigma, which is this point, then probability of x less than or equal to m plus sigma will be 1 minus q of 1. Okay. That means it basically indicates the area under this curve for values less or equal to m plus sigma. Beyond this, below this, all the area below this point. Okay. So likewise, if I take this point, which is m minus sigma, and I take the probability of x less than or equal to m minus sigma, and that will become 1 minus q of x is m minus sigma. This x is m minus sigma. So you get m minus sigma minus m. So your m get cancelled. You get minus sigma by sigma, that is minus of 1, q of minus 1. Or I can write it as 1 minus, and q of minus 1 is 1 minus q of 1. So you get it as q of 1. Okay, because this 1 and this minus 1 get cancelled, and minus 1 and 1 becomes plus 1. Now this will indicate the area that you will get for x having a value less than m minus sigma, which is this point. This is m minus sigma. So probability of x having less than or equal to m minus sigma is this area. Okay, and the probability of x having value less than m plus sigma is the area below this point. Okay, of course including these 2 points. And if I want to find the probability of x between these points, m minus sigma and m plus sigma, then I simply subtract this area from this area. Okay, and if I subtract this area from this area, I will find the probability of x lying between m minus sigma and m plus sigma, or I can write it as the probability of x minus mean of x is less than sigma. Okay, so if you subtract the mean from x, then that will be less than sigma. So under this condition, your x minus sigma, your x will basically lie between m plus sigma and m minus sigma. Okay, this will become simply, I simply subtract this from this. Okay, because this gives me the area of this PDF from minus infinity to m plus sigma, and this gives the area from minus infinity to m minus sigma. So if you subtract this, I will left with this portion, which is the probability of finding x between m minus sigma and m plus sigma. So that is 1 minus q of 1 minus q of 1, which becomes 1 minus 2 times q of 1. Okay, so this is 1 minus 2 times q of 1. And if you look to this q of 1 from this equation, the q function for x is equal to 1, it is 0.1587. Okay, so it becomes 1 minus 2 times 0.1587, and that comes to be around 0.68. Okay, it means the probability of the random variable x, the Gaussian random variable x, having a value between m minus sigma and m plus sigma is 68%. So 68% of the values of the random variable will lie between m minus sigma and m plus sigma. Okay. Likewise, if you take this point as m plus 2 sigma, then definitely you will get here 2, q of 2 and q of 2 here. If you take m plus 3 sigma, then your m and m get cancelled. You will get 3 sigma by sigma, you will get q of 3. Okay. So I can say the probability of x minus x bar is less than 2 sigma will be equal to 1 minus 2 times q2, and you can look for this q2 function. You can put here, you will get 0.94. Likewise, the probability of x minus x bar, probability of this less than 3 sigma is 1 minus 2 times q of 3, which is 0.9974. Okay, this accurately is 46. This is 268. So what you get from this equation, you basically try to estimate the width or the spread of the Gaussian random variable. Okay, so if you take the range of the random variable between m plus sigma and m minus sigma, okay, or m plus minus sigma, you get 68.2%. So for m plus minus 2 sigma, it is 95%, and for m plus minus 3 sigma, you have 99%, or 99.74% exactly. Okay, it means if I take here a Gaussian random variable which has some mean m and which has some variance sigma square or standard deviation. So if I take a width of m plus minus sigma, this is m plus sigma, m minus sigma, the total width is 2 sigma. So 68% of the samples will lie within this region. Okay, and if you take m plus minus 2 sigma, that means your total width is 4 sigma, then between this you will get 95% area. Okay, and finally if you take m plus minus 3 sigma, which is total width in this case is your 6 sigma, so you get 99.74% of the values. Okay, so it means the total, you can say roughly the total width of the Gaussian random variable is basically 6 sigma. Okay, because beyond this you only have 0.26% values which are left. 99.74% of the values which the random Gaussian random variable will take, they will lie between this range, mean plus minus 3 sigma. So if I take, suppose mean is, let us suppose we have a mean of 2 and you have variance is 1, then I can say that if mean is 2 and the variance is 1, so this is the mean value 2, and if sigma is standard deviation, sorry, not variance, if standard deviation is 1 and of course the variance is also 1, so mean plus minus sigma, that means you can say that 2 minus 1, 2 plus 1, between minus 1 and plus 3 you will get 68% probable. The probability of finding the random variable x between minus 1 and minus 3 is 68%. Okay, likewise m plus minus 2 sigma, and sigma is here 1, so it means when you take sigma is equal to 1, then minus 2 sigma becomes 0, 0 and 5, you can say. The probability of getting the random variable between 0 and 5 will be 95%. Okay. And similarly, plus minus 3 sigma, between minus 1 and 2 plus, 2 plus, it will become 4 initially, not 5, sorry, because it is mean plus minus 2 sigma. So mean is 2, minus 2 minus 2 is 0, 2 plus 2 is 4. Okay, and if you get m plus minus 3 sigma, then it will become 0 minus 3, that is minus 1, sorry, 2 minus 3 minus 1, and 2 plus 3 becomes 5. So probability of getting the random variable between minus 1 and 5 will become in that case 99.7%. Okay. So that is the important property of the Gaussian random variable. So once you know the mean and the variance, you will know that the total width of the Gaussian PDF is mean plus minus 3 times sigma, or it is equivalently 6 sigma is the width, because 99.7% of the values they will lie between this segment. Okay.